Hello everyone. In this class I will discuss about writing R programs or code to compute indiscernibility relations, to compute set approximations, and to convert information table into decision table. And obviously before that I will create an information system or a table in Microsoft Excel, and I will show how to load it in R program. In my earlier video I already discussed various theoretical aspects of some of the concepts of rough set theory, such as information system, then indiscernibility relation, the set approximations. These all I discussed in my earlier video. And if you can remember, I also discussed with an example how to compute the indiscernibility relation, then how to compute set approximations, lower approximation, upper approximation, then boundary region. Okay, so all these examples I have shown in my earlier video, and I took this example. There are three attributes: age, lamps, and walk. And age and lamps are conditional attributes, and walk is the decision attribute. That these are the things which I discussed in my previous video. And I also discussed how to install R and RStudio. Okay, how to install R and RStudio, then how to work, how to set working directory, then installing packages and libraries. Okay, these all these I have shown in my earlier video. Now, if you do not know R, or if R is not installed in your machine, then you can go back and you can see those videos. Installing R and working with R is very simple, and anybody can start working in R. So we are now in Microsoft Excel, and I will create a table here. So a table is already, the partially created here. We have 6 objects. So let me add one more object here. Let me add P7, and so let us say this is my table. This is my information system which I have created in MS Excel. Now let me save it. Let me save it in as a .csv file. So this is the location D rough set using R. This is my folder. In this folder I am saving this Excel file as .csv file. Okay. Now let us move to R or RStudio and start our programming. So we are now in RStudio, and let me open a new script. Okay, so here I will be writing the commands. So first let me save the script, and I will be saving it as first .r, and I will save it in drive D, and the folder will be this one where the table is already created. So the script is saved. Now first of all I will set the working directory. Set working directory, and I will give the name of the path where I have saved my table, D, and okay, within double quote I have to give it. So this is simply telling R that all my files and related documents are saved in this location. Now you can make your own directory, own location, and just you have to mention here. Now let us see how to execute this line. Keep your cursor on the line and click the run button. You can see the line is executed and there is no error. So the execution result we can see in this window. Okay. Next we have to install necessary packages. So for this, install.packages, it's coming here. Now I'll use, or I have to use a package called roughsets. Okay, so this is the package I'll be using, and then library and name of the package again. Okay, now to install this package you need to be connected with the internet. So I'm already connected with the internet, so let me execute this or install the roughsets package. Click the run button. See, it is executing now. I mean, the package is being installed here in this machine. See here, the package is now installed in my R. Now we need to load this package in this program. Okay. Next, we need to read the table which we created just now. That table, that information system, we need to load in our program. So for this, I'll create a variable info table. In this table, in this variable, this is the variable. In this variable, I'll store the information system. So for this, I can use a function read dot table. So this is the function which will fetch the table which is in comma separated or CSV format in this program, and we have to mention the name of the file, name of the table. So I named it as work dot, the extension is CSV. Then I have to put here the header information. That means header equals to true. That means we not only want to read the rows, but also we want to read the column names also, the features also. That's why the header equals to true. And separator, in case of CSV file, we need to put separator as comma, because in a CSV file all the values are separated by commas. So now execute this line, keep the cursor here and click the run button. So this table is read. Now if you want to see the table whether it is fetched or not, simply you can print the content of this variable, because after reading, the table has come now in this variable, is assigned to this variable. So now let us print the name of the variable. So here you can see, after I executed this line, this is my table which I created. It has 7 rows and 4 columns, and I will consider this work, the 4th column, as my decision column, and column 1 and 2 as my conditional attributes. Now let me delete this line. Now I will convert this information table into a decision table. So for converting an information table into a decision table, we need a function that I will be using now. So let me take a variable first. So let me take decision table. You can give any suitable name for a variable. So since I will be converting this this information into a decision table, so now the function name is sf dot as decision table. This is the function which will convert this information table into a decision table. Now here I have to mention, see, you can see here we have to give the table name. So this is my table which I am to convert. Next I have to give the decision attribute. That means I have to specify which column will be considered as decision column. Now I will make work the 4th column, 1st, 2nd, 3rd, 4th. So the 4th column will be my decision attribute. So here I have to mention 4. Next I have to mention here the index dot nominal. Now here 2, 2, 3, let me do it. So now column 2 and 3, here you can see here I'm just considering column 2 and column 3, first, second, third, first, second, third, fourth. So this second and third, these two are considered as conditional attributes, and I have to mention those two attributes. Now if you want to make different columns, accordingly you have to make the changes. Suppose you want to make the third and fourth as your conditional attributes, so you can change here. Now let us execute this line. So this line is giving no error, it is executed. That means the table is now, information table is now converted to a decision table, and it is stored in this variable. So if you want to see the content of this variable, simply select it and click on run. See, it has come again. So it is now internally a decision table, and we have mentioned that this fourth column is the decision column. Next I will compute the indiscernibility relations, and the result, the indiscernibility relations, will be saved in a variable. So let me give a name ind. I created a variable ind where the indiscernibility relations or the equivalent classes will be saved, and for this I will be using a function called bc.ind. See, this function I am going to use, which will take the decision table. This is my decision table. Okay, so this table I am giving as parameter, as argument, comma. Next I have to mention the feature set. That means the set of attributes based on which the indiscernibility classes will be computed. So here I will compute indiscernibility relations based on the second and the third attribute. Okay, if your table is different, if you want to make your indiscernibility relations based on different attributes, then you have to mention those attributes in this part. Okay, so let me execute this line. Yes, it is executed and there is no error. Now our indiscernibility relations are computed and it is stored in this object, in this variable. So if you just want to print it, print ind. Okay, now if I execute this line, this print, see, now the result has come here. Okay, see, I executed this line, print, and we have the following indiscernibility or equivalent classes. So the first equivalent class, the object 2 is in the first equivalent class, object 6 is in the second equivalent class, object 1 in the third equivalent class, object 3 and 4 in the fourth equivalent class, and object 5 and 7 are in the last equivalent class. So these if you can if you want to check, if you see my earlier class, there I computed those equivalent classes and the result exactly matches that. You can verify that. Now if you want to check what these functions are, okay, suppose you don't know about this read.table function. Okay, what does it do? If you don't know about this particular function, then what you can do, you can simply type help and type your function name. Okay, suppose I want to know about what is sf.as decision table function, what does it do? So simply type help, and now if you execute it, run it, see here you will get the complete description about this function. What does sf.as decision table function do? Okay, you can read the complete documentation. Now this function is available in roughsets package. Okay, this is the name of the package in which this function is available. And what does it do? This function converts data.frame into a decision table object. Okay, So this function converts something into decision table, okay, and all other related documentation is available here, okay. In fact, how to use it, an example is also given. So in this documentation you can get the complete description. Similarly, if you want to know about this function, what does it do, bc.ind.relation.rst, actually this function what it does, it converts this decision table with these two attributes, and using these two information, using a decision table with this feature set, it converts or it computes the indiscernibility relation, which is now stored in this int variable, okay, and you can print the result. Before I write code for upper approximation, let me show you the result which we obtained in one of my earlier video for upper approximation for various approximations. So this is the result which we got, and we approximated the set W, where W is equals to x such that walk of x equals to yes. That means we approximated the objects belonging to yes class. And in my R program I will also show how to get the approximation for W for walk of x equals to no, that means for no class also, okay. So the various approximations you can see here, the lower approximation, upper approximation, boundary region and outside region, and based on the definitions of lower and upper approximation. So let me take a variables, and I will use a function called bc dot lower upper approximation, and as argument I have to give the decision table and the indiscernibility relation which we computed already. So we need two things, the decision table and the indiscernibility relation as argument to this function. So this function will compute lower upper approximation. Let us execute this. Okay, now there is no error, that means we have computed, and let us see what is there in this variable. Print and variable 1, okay, execute. So this is the result. So you can see various approximations, the lower approximation with respect to the yes, class, object 6 and 1 belong to lower approximation, and upper approximation when the decision is yes. So object 1, 2, 3 and 4, these are the objects which belong to upper approximation, and when you come to no decision, the lower approximation gives 2, 5 and 7, and upper approximation with respect to the no class. So these are the objects which fall in the upper approximation when the decision is no. But where are the boundary region and be outside region? Let us see if we can compute those also. So this function bc.lu.approximation, this function computes the lower approximation, upper approximation for both yes and no class, but they do not show, I mean this function do not give us the boundary region, the outside region. Now we will compute these in this program. First I will compute the, I will show you the, I will separate the lower approximation. So let me take a variable, say low yes class, okay. So my result is stored in this variable. So this variable, the lower approximation and for yes decision. So now if I execute this line, okay, let me show you what I get here. So the result is here. See, the lower approximation has two objects 6 and 1. Now the upper approximation, I will take another variable, say with respect to yes. So this is a variable name. You can give your own variable name, and variable 1 the yes. Now execute it and let us see what is there in this variable. See, in upper approximation we have object 1, object 6, 1, 3 and 4. So these are the members of upper approximation. Now what is boundary region? So we know that boundary region means upper approximation minus lower approximation. So we will use a function set difference, and in this function I will give the upper approximation comma the lower approximation. Okay, so the lower approximation is this, and that I can store in a variable, say approximation. Okay, now let us execute this. See, so in boundary region we have object 3 and 4. So this is same as we got earlier. Now what is outside region? Now the outside region, for outside region we have to subtract the upper approximation from the universe. So what is our universe? So let us take a say U represents the universe, U equals to so we have to take all the objects. Okay, 1, 2, how many rows? N rows of decision table. So what I am doing, I am taking 1 to n rows of decision table. So how many rows we have? We have 7 rows or 7 objects. So U will have 7 objects, 1 to 7. So let us execute it. And what is in U? U has 1, 2, 3, 4, 5, 6, 7. So this is our universe, and so to compute the outside region, so let me take a variable outer equals to set difference, because we need to find the difference between U and the upper approximation. Okay, so this should give me the boundary region. Let me execute it. Executed, and what is in this? See, object 2, 5 and 7. These are the 3 objects which I have in boundary region, the outer region. So object 2, 5 and 7 we have in outer region. So here I have shown you the approximation for the yes class. Okay, now if I simply change from yes to no, okay, now we will get approximation for the no class. See, we have changed from yes to no. Let me execute it. Okay, and let us see what is in this variable. See, the lower approximation. Now here I can change the name of the variable also, from yes to no, from yes to no, and boundary approximation. Okay, fine. Now here also the variable name I have to change from the same variable I have to give here also. Okay, and outer region. See, the outside, the upper okay, so let me execute these lines once again. So we have in this variable we have the lower, upper, all the approximations, and in this line I am computing, in this particular line I am computing the lower approximation with respect to the no decision. In this line, upper approximation with respect to no decision. in this line upper approximation. Actually we have to find upper approximation minus lower approximation, so this part will come next. Okay, so set difference finds the difference between these two sets, upper approximation and lower approximation, so the boundary region will be obtained here. Next we have the universe in this, and the outer region will be the universe minus the upper approximation. So let me execute these lines one by one. Okay. Okay, now the result is computed. Let us see the content of this variable. See, the lower approximation for decision no, object 2, 5 and 7. The upper approximation for the decision no, these are the objects we have in this upper approximation with respect to no decision, and the boundary for no class. See, the boundary is again 3 and 4, object 3 and 4 falls in the boundary region, and outside region for the class no, we have object 1 and 6 in the outside region. We have come to the end of this video. These are few references you may follow.